Has returned to the grand finale of this exceptional workshop will be presented by Roei. No pressure.
Are we set up? We are set up. 1 second. Okay. Hi, everyone. Pleasure to be the last talk in this wonderful workshop. We're going to talk today for something like 45 minutes about uniform version of hardness versus randomness and some progress in this. And it's based on a joint work with Ligia, who is here, and let's pretend that he's here in the audience too, and with, oh, hi, Ligia. And with Ron Rothblum from the Technion. So let's remind ourselves of some context, okay? If we want to deduce the randomization, BPP equals P, ignore promise issues, hiding things under the rug here. So we can use classical hardness versus randomness stuff. It's enough to assume circuit lower bounds, right? Non-uniformity cannot speed up the computation of arbitrary problems in exponential time. That's in Pagliazzo-Witterson. And you can use these new non-black box hardness versus randomness frameworks and like make do with the hardness on almost all inputs. Like there's a function computable in polynomial time and mile depth, like n squared, that's hard for probabilistic time, something fixed polynomial on all but finitely many inputs. And these are strong assumptions, as you'd expect. The second one, or at least variations of it, is also necessary. So we're happy. But the motivating question for what we're going to do today is, okay, what happens if we're willing to settle for less? We want to make do with weaker, normal, humanly parsable assumptions. Okay, and so let's settle for derandomizing on average. And the notion of average throughout this talk will be success 99%, or 1 minus 1 over n over the uniform distribution. So it's a very weak notion. And the goal is to optimize the assumption, get something normal. Maybe standard hardness, worst case hardness for probabilistic algorithms or something like that. Maybe even something that's intuitive, that we can understand, or at least imagine that we understand, and it's weak. This is a context that kind of unites 3 different lines of work in this area, which were separate so far. One that was started by Russell and Avi 25 years ago. Another one that was started by Avi and Oded Goldreich 20 years ago. And another one that isn't a line of work, it is a work, but it's separate and related. It's by Marco, Russell, and Manuel Sabin from 4 years ago. 5, time flies fast. So part of what's going on here is that we're going to unite them all and give them one context. Let's do, it's like an action movie, right? We need to start with an action sequence, then the exposition. Okay, so this is the action sequence. It's like jumping ahead. This is a sample theorem. Here's the sort of thing we're going to do today. So assume that counting k clicks on an n vertex graph takes probabilistic time n to the log star of k. Right? Not n to the k, n to the something that grows with k. I don't care how weakly it grows. Then RP equals P on average. The notion of average is 99% over the uniform distribution. What I find interesting in this statement, we're going to prove more general versions and stronger stuff, etc. But what I find interesting here is that I can understand the assumption, or at least I can imagine that I understand it. Right? K clicks, n to the k, how can we optimize n to the log star k? It sounds very believable when I look at it. And that the conclusion is surprisingly strong. Because the assumption looks like really appealing to me, like, oh yeah, sure. And the conclusion is suddenly like, okay, polynomial-time derandomization. Maybe of one-sided error. Maybe with like error on 1% of the inputs, but still, I wouldn't have expected that.
Sorry, can you clarify?
Yes, we're going to have a rug and stick it under the rug. But this holds almost everywhere, no problem. Like in this particular aspect, all the results today will actually be good, but I want to hide it like promises, IO versus almost always, everything, just not talk about it because there's a lot of details there.
Right?
Yeah.
What's the fastest algorithm we know for counting k clicks?
I don't no, I'm not a K-click.
Oh, okay.
Someone do this. Is there a K-click person in the audience?
Into the omega k over 3, where omega is major smallest. Yeah.
Well, and what is omega today?
Well, I have to ask somebody else in my family.
Yeah, my kid, right?
So actually, like, okay, so n to the k over 2, we don't know. And if it would have been n to the k over 2, like the right answer, then the result from like Marco and Russell and Manuel Sabin would have already been enough.
I see.
This is like something that.
If counting click is counting BPP, that is good. So what's the connection to that?
What do you mean BPP?
I mean, you make k equals 4 complex, like something greater than it. And then if CFK equals to k, it's essentially saying that counting k is not.
So I need to be careful here because for the upper bound, I'm relying on something that's parallel or low degree or something like that. And if counting clicks is like for something that I can't do efficiently in parallel, because it would be large, then we're gonna have
Oh, I see. So the sum.
yeah, we need a problem in a certain subclass of P that's hard for fixed probabilistic. But I'm going to provide a formal statement later, or maybe that will answer it.
But I guess my question is for which k is this relevant? For which?
Okay, so if you want to be formal, if for every C there exists k such that counting k would take time more than n to the C, then. Okay, we move past the action sequence. This is our plan for today. I'm going to start with something boring and weird that's really important. It's a classical missing piece in hardness versus randomness. Basically, something doesn't scale as we think it should scale. We've been stuck for 25 years on it. This is the first substantial progress that, as far as I'm aware of. And while it might be okay, so something scales, I mean, fine, we've been stuck for a long time. Maybe that's not the most appealing thing, but I'm going to talk about it in depth. And this will be what we need to make progress on natural and intuitive stuff, such as counting k-clicks versus derandomization. So it's going to be important. Then I'm going to talk about natural and intuitive stuff, like counting k-clicks, and more general problems. And I'm going to end by giving some constructions and proof ideas of what's going on here. And let's start by something that I have demotivated you about, a classical missing piece in hardness versus randomness. So the context now is not the new non-black box versions of hardness versus randomness. We're going back to the 90s, okay? Classical hardness versus randomness. So the main focus of the classical stuff in textbooks that we teach and write about is a formal equivalence between lower bounds for circuits and PRGs for circuits. For example, the classical result of Russell and Avi following Simon Wigderson, like, okay, exponential time is hard for circuits of exponential size if and only if there are PRGs that would give you BPP equals P. And we also note that this scales. There was a lot of work put in to make it scale well. That work was put in the late 90s and early 2000s, and it was successful. So let's parse this, okay? We're starting with a function computable in exponential time, which is an intuitive thing to do when you do randomization because you're going to compute the entire truth table, so exponential time. And what is the hardness that we assume? We can assume hardness for all polynomial size circuits, and we can increase the hardness maybe up to exponential size circuits. And as we increase the hardness, the randomization that we get from it becomes faster in a smooth way. Like if it's hardness for poly-size circuits and you get 2 to the n to the epsilon time, if it's hardness for exponential size circuits, you'll get BPP equals P and you're happy, and don't parse this. It's a smooth thing. And the point that I want to make is that there is a second line of works in hardness versus randomness that does something different. It shows an equivalence, hiding IO versus AA under the rug, between lower bounds for algorithms, just normal probabilistic algorithms, not circuits. These are a bit more natural and weaker lower bounds, and average case randomization of BPP, such as the one we're talking about today. So for example, again, a 25-year-old result, exponential time is hard for BPP, if and only if BPP can be derandomized in sub-exponential time on average. This is the type of thing in the secondary line of work in hardness versus randomness. And when I started my PhD, I kind of assumed that hardness versus randomness is done. Like we know everything, right? This is a rug. We are hiding stuff underneath it, okay? Don't ask about infinitely often, almost always. Don't ask about the distributions over which we're average case I'm being fair. I'm hiding good things and bad things in equal amount under the rank. Okay. So this is what you'd expect to be true for the uniform setting, hardness for algorithms versus average case randomization. The same thing you put in, you'd get in the end. You can also show that it's necessary. So it should be obvious that this is what's true, except that what we know is still the same thing that we knew 25 years ago in the original work. Something like this. As you increase the hardness, the best thing that you can get is like half exponential time in the randomization. And, okay, I'm going to talk like for a while today in this lecture, and in the end, for the general setting, we're still going to remain with this picture. So like if you remember something, remember this open problem, which is great. I mean, okay, something doesn't scale. How come it's been 25 years and we don't know how to scale it? There's an interesting technical problem. Let me explain what this technical problem is, okay? All the proofs in this line of work go by reconstruction arguments. If you can break the PRG, you can compute the hard function, right? The function is hard, you can compute it, fine, the PRG is secure. That's the main idea. And like if the reconstruction argument hardwires some non-uniform advice, then if we break the PRG, we compute the hard function with a circuit, a non-uniform circuit. Assume circuit lower bounds, you're done. This is the main line of work. Now, if we only want to assume hardness for algorithms, we want to make sure that the reconstruction here is totally uniform, doesn't hardwire any non-uniform advice. Okay, so a uniform reconstruction argument and the only problem is that we don't know how to do it. For an arbitrary function in exponential time, the uniform reconstruction is highly inefficient, what leads us to this half exponential thing. Okay, there's a classical idea on how to overcome this. The classical idea, it's already implicit in the original work. It was crystallized later, like most prominently by Trevisan and Vathan. Instead of assuming hardness for an arbitrary function in exponential time, let's assume hardness for specific functions that we can actually work with. They have nice properties, downward self-reducible and random self-reducible. For example, the permanent satisfies this. And also there are other constructions of nice functions that satisfy this, more artificial ones. And then we know how to do this uniform reconstruction because we have the nice properties and we're leveraging them. So for example, like Ligeron and I, and also with Eilon Yogev a couple of years ago, really crunched the parameters of something along these lines and got something like this. So instead of exponential time, fix a specific function in p-space. It's a TQBF, totally quantified Boolean formula, some p-space complete language. Assume hardness for this function specifically. Then you get something that's kind of nicer, maybe. Okay, you get a bit of better parameters. Totally, like everything's quantified, every single event. This T or that T? This, okay, yeah. And okay, it's a specific function, and notice this is the polynomial thing, so we're not getting it. We got like n to the polylog log n. So fine, this is what was known. The limitations of the previous classical idea was that such functions with nice properties exist only in p-space, provably. Even if you relax the nice properties, it's still in subclasses of exponential time. Can't win. Also, these are specific functions. So either you assume hardness for this particular function, or you assume hardness for something else and reduce to this function, paying polynomial overheads and losing in the derandomization. These are your two choices. The third problem is that the known functions with the nice properties are easy, or they're not really easy, but they're solvable in less than exponential time. You would never get polynomial time derandomization from these functions. They cannot be exponentially hard. And the fourth problem is that all the previous arguments incurred runtime overhead. So even if you would solve all of this, you would still not get polynomial time. And the main contribution in this weird classical missing piece part is this. Okay. It's something that's better. It's not optimal. We haven't nailed it yet. The problem is still open, but there's progress on stuff that we really didn't know how to make progress on. So what's going on? This is a class. It's not one function. And this class probably it contains linear space and probably extends far beyond p-space. So we broke through. That's good. And we get polynomial time derandomization. Any function in the class would do. It doesn't need to be a specific one. And also these functions can actually be exponentially hard, right, in contrast to the previous known ones. And the sad part is that it's only the randomization with one-sided error. It's basically only RP. Let me state this formally. So the class would be the class of functions computable in exponential time and depth 2 to the little o of n. So log space uniform circuits of size 2 to the n and depth 2 to the little o of n. And like if you have exponential hardness, then you get polynomial time derandomization, and it scales quite well. Not perfect because we have this little bulge here, but forget about it. That's not. There's still a lot of work to be done. This is only for RP. You can do BPP, but you need to pay some advice. So like if you want to do polynomial time derandomization, you're paying logarithmically many bits of advice. It's not perfect. Note that this class contains linear space, right? By repeated squaring the matrix, you can also always simulate like linear space in like size 2 to the n and depth, I don't know, polynomial, right? Let alone 2 to the little of n. So this class seems much larger than P space. And we don't need any special structure of any function there. Any function in the class would do. Conceivably, this class should have functions that are exponentially hard, and we get polynomial time derandomization. The sad part is only one-sided error. It's not fully exponential time. The trade-off has a bulge in the middle. So that's basically it. That's all I wanted to say about the missing piece in hardness versus randomness, the classical stuff. We got some progress. The point here isn't that we're done. I'd like to still highlight the open problem. We're not done yet, even with classical hardness versus randomness stuff, even though we're moving towards the new non-black box approaches. So I'm highlighting the open problem. And the fact that there is substantial progress here on stuff that we didn't know how to do for a long time is what paves the way for progress on what I'm about to show next. Any questions before I move on? Yeah, Marco.
That size depth class without the log space uniformity.
Wait, that would be very sad and interesting if I know how to do it, because actually we don't have to do complicated stuff to avoid it. Good questions. Yeah, questions. Okay, let's talk about randomization from intuitive stuff. The motivating question is, can we reduce randomization from stuff we understand? And of course, the nicest setting is fine-grained hardness in P, because we feel like we understand problems in P better than exponential time. So now we want to reduce the randomization from fine-grained hardness in P. And the main point to highlight here is that this question means that we're trying to do something harder. Because hardness up there in exponential time is a stronger assumption than hardness below in polynomial time. So right now we want to deduce the randomization from weaker assumptions. Intuitive, natural, we can understand, but weaker. So we're going to need to work a bit. And in particular, the results here build on the results before with some extra improvements. There's one line of work called typically correct randomization, started by Oded Goldreich and Avi Vigerson 20 years ago. Their original intention was different, but it ended up showing things like this. So this is by Clevens, by Milkabek, and Shaltiel. No, sorry. So it's yeah, thank you. Sorry. So here is a result. Assume that for every constant C, there is a language in P. It can depend on C, right? So this is like C, and this is n to the 100C, the running time, or something like that. That's hard for circuits of size n to the C, where the hardness is like mild average case hardness. Every circuit fails on like 1 over n of the inputs. Then BPP equals P on average. What's going on here? This is a very clean result of the type that we are looking for. This is just fine-grained hardness in P, a problem in P that's hard for time n to the C, right? The most general thing you can imagine, but the hardness is for non-uniform circuits. Our entire goal here was to get rid of non-uniform circuits and stuff that we don't understand. This is the drawback. And also we need some mild average case hardness, like every circuit fails on like 1% of the inputs, or 1 over n.
Just using some resistant to get P equals P. I mean, just basically some resistant to a hard function.
How would you quantify the hardness?
Oh, so you need to work. Yeah, you need to work. But you need to actually solve. That's what I assume.
Yeah, starting with random, exponential, I don't know.
Well, some version of an average case on assumption for B and plus B.
And if you're starting in P, generally, you're not going to end up in E, you're going to end up in X. So like with what you're saying, maybe you can get sub-exponential or quasi-polynomial time.
Anyway, I think. Yeah, that's,
I mean, that would be interesting nonetheless, regardless of it. The goal here would be to get a uniform analog of such a thing, right? If I know to say, oh, there's a function in P that's hard for probabilistic time n to the 20, and that gives BPP equals P on average, I'd be really happy. That's a clean statement. A uniform hypothesis is also necessary for such a thing. So great. The other line of work, it's called, it is a work, Problem-Centric Derandomization. This is a work I mentioned by Marco Russell and Manuel Sabin. This is, there are a couple of results there. This is one of them. It's representative. Assume that for every k, counting k clicks is hard for probabilistic algorithms running in time n to the k over 2, basically. Okay. It's great. This is enough. BPP equals P on average. It's great because like it's only worst case hardness. It's for probabilistic algorithms. It makes sense to us. But it's really the upper bound and the lower bound are tied together, n to the k versus n to the k over 2. And it's a specific problem. It's not a family of problems. There are a couple of problems that are very specific here you need to assume hardness for the same reason that I talked about before in this classical missing piece thing. These problems have this type of downward self-reducibility and random self-reducibility properties, at least when you arithmetize them a little bit. So that was the reason you needed these specific problems.
Sorry, this looks very close to what you had at the beginning, the action sequence. Can you just compare this to your action sequence?
Of course, in the action sequence, you need the hardness. I don't know where to look. You need the hardness to grow like as any growing function of k, like n to the log star of k. Here you need basically n to the k over 2.
Okay.
Does that make sense?
So that's the main difference. Okay.
Yes, well, I'm going to show something more general in a second.
Okay. Okay. Thanks.
Inclusion, like it's, you still get just derandomization.
RP instead of BPP.
Oh, RP, that's what I was thinking.
Yeah.
So for example, ETH implies your hypothesis, but not ours.
Okay, didn't notice that. Good
I mean,
point.
it's effectively like saying counting k clicks is not FBT.
Yeah, I didn't know that. True. Very cool. Okay, but I'm going to show again something more general than that. Give me a second. Okay, so let's what we want more general functions than these specific functions. So assume that here are two theorems. Okay, the first is assume that for every c there's a function computable in polynomial time and depth n squared. LU is log space uniform. Forget about uniform circuits. Polynomial time and depth n squared. That's hard for probabilistic time n to the c with this mild average case hardness. Then RP equals P on average. This gets close to what we want to get in the by analogy to the non-uniform setting, except that we're restricting the depth to be n squared. I'm not really sure how to eat and parse this statement, except that it's nice and it compares to the non-uniform one. So I have something that's more intuitive now. Assume that for every c, there's a function computable by arithmetic formulas of polynomial size and degree n squared over a field of large polynomial size. That's hard for probabilistic time n to the c. Let's parse this slowly. This is like the punchline here, okay? This contains stuff like k-sum, k-click. You can always just count in parallel, like arithmetic formulas. But this is likely a much more general class. It can solve all the problems that you can just brute force and count, but it can solve many other things. If there is a function in this class, any function that's hard for probabilistic time n to the c, like for every c you can find the function, then you get RP equals P on average. And the k-click example was just one instance here.
So the k-click example is supposed to be a special case of this?
It is a special case of this, yes.
Oh, okay. Well, so then that means that this is some language. So you're thinking of arithmetic formulas taking in binary, and then you construe the output of that arithmetic formula as an
You can add a gadget on top. Like I didn't mention it, but add the gadget on top.
It's not a language, right? It's a
No, it's
you can
not a
make it
language, it's a function.
Oh, yeah, okay.
It's a function. So you either get the field element in the end, or you do some simple manipulation to field elements to get whatever you want.
Okay.
You can do it with languages too, but it doesn't have to be. Any other questions? Okay. I'm gonna move on. Yeah, no, please.
I mean, is it going to be difficult for you to explain how to see that the K clique is a special case here?
Fix K, K is like 3, right?
Okay.
It's like degree 3 stuff, right? Just to test all the clicks and sum them up.
Yeah, it's only the end of the order one. That order one can depend on like C.
Yeah.
So there's enough, whatever,
Right.
to store the number of cliques.
Does that make sense? Yeah. It's probably much more general. I didn't say degree like constant, degree n squared. Yeah.
So the hardness is for two-sided error probability, or for one-sided.
Good way. I think for two-sided. Let me think for a second if I see a way to do reconstruction in a one-sided way. I don't. Hardness for two-sided error. The rest will be like proof ideas and stuff. Okay, let's do proof ideas and stuff. This is a proof idea of how to deduce this result easily as a black box from the previous one. Let's do it because I think we have time, okay? Assume that I already convinced you of this thing because the paper is published, so it's probably true. Okay? So this thing is true. So now let's prove theorem 3 based on it. So we're starting with a low degree formula, like a formula of degree n squared. You know that you can balance formulas. If the degree is n squared, probably we can do it in small depth too. Just balance it very efficiently. Keep it small degree, keep it log space uniform. So now let's assume that we have like n squared, probably much lower than that, right? But let's say n squared depth formulas. Great, we're already at the set close to the setting before, because now everything has depth n squared. And now we just need to amplify worst case hardness to mild average case hardness, but that shouldn't be hard because we're arithmetic already. It's a low degree polynomial over a large finite field. So just, okay, we're done. Yeah? Okay, we got mild average case hardness. That's it. There's some details here, but that's the plan. And it doesn't go wrong too much. Great. So now all I have to convince you is of theorem 2. Yeah. So.
Can I just ask you a high-level question? Like, so you've proved theorem 2. Like, what would you like want to prove next here? Like, what would be?
Remove the n squared.
I see. And that seems very difficult.
Even with like a necessary condition for that is to remove the 2 to the little of n in the classical missing piece thing. I don't know how to do that.
I see.
So,
All you got.
oh yeah. Okay. True. Get it to scale nicely. There's an open problem set. All right, let's put theorem 2, okay? The basic building block was something from a previous work with Lige. It's like something we did for non-black box derandomization. It's what Odin Goddard defined as a targeted heating set generator. And this is the construction for a previous work. I fixed parameters so that things would be nice. Let's derandomize linear time, just to have fun. Okay, so for every function in like that has computable in time n to the 100 and depth n squared, right? There is a corresponding targeted heating set generator. The function was f. The heating set generator depends on f, so it's h sub f, and it satisfies the following: the heating set generator gets an input x, reads the input, and prints a list of n-bit strings that depends on the input. And the guarantee is the following: for every linear time machine M and every fixed input x, so now we fix the input available to all parties. If you can break the PRG on x, then you can compute the hard function on x. Okay, if the heating set generator doesn't hit the linear time machine, and the linear time machine tends to accept all strings, the standard notion of not being pseudo-random for a heating set generator, then there's a fixed algorithm that depends on the machine, runs in time n to the 10, and manages to compute the function on this particular input. So breaking the targeted PRG when it's targeted to that input means computing the hard function when the input to the hard function is this particular one. And it generalizes. We're going to use the same thing in the exponential range. Let's ignore this. The key points here is that hardness on an input means pseudo-random on the same input, and that any function in the class would do. We don't need any special properties other than being in this class. So here's the plan, and here's where it will go wrong. It's kind of where we started from. Like, for sure it should work, except that there's a missing part. Let's just use it, okay? Let's start with a function that's hard in the worst case. Now do all the usual tricks that we know how to do in complexity theory and get a function that's hard on 99% of the inputs. So worst case to average case reductions. And then just feed it to the targeted heating set generator, and that's it. The second part works, no problem. The first part it was not known. Now, I'm not saying that this is something like inconceivable, because we're going to do it in a second, but it did require new technical tools. Okay, so this is still the high-level plan, and the main technical contribution going forward would be to show this type of thing: worst case to average case reductions that are hopefully optimal and hold for the relevant classes.
So under standard cryptographic assumptions, not exponential time cryptographic assumptions like learning with errors, you can get these things generically. How would this compare to such statements?
I don't know what learning with errors would give you here.
Okay, no, okay, you need to.
It has to be like a
change F to G.
multi-output function with a lot of output to even possibly be hard.
Yeah. Okay. When you can use Polimorphic Encryption or even other cryptographic assumptions to take an F, so replacing F by G will not be good enough?
Yeah, by G is okay as long as it's in the same class. Basically.
Yeah.
This should be F prime, really. That's not the issue. So you're saying that certain assumptions.
Just as a statement, suppose you could prove your conclusion, but throw in an assumption that LWE is hard in the usual case. How would that compare? It would be more specialized, but then.
So listen, I'm interested in knowing more about it. I don't want to do it on my feet. However,
you're using polyomorphic encryption to do random self-reduction, not random.
Yeah. Okay, I just want to mention that like one bit that I don't need fully homomorphic encryption because this is unconditional. Yeah. But I want to know about it regardless. Okay. Okay. What we're going to show is just unconditional results. So we're going to start with worst case assumptions. Okay, let's see where things break when we want to do worst case to average case reductions without this what the fully homomorphic encryption will do that I guess. So it's in the usual way. Start with a problem such that every n to the 20 algorithm fails to compute it on a small chunk of inputs, like 1 over n, and code the truth table of that function to another truth table by an efficient, approximately locally least decodable code, the standard thing that we know how to do. And if this sounds like mumbo jumbo, do direct product. Take a direct product, okay? No problem. Do it multiple times. And now, like if the original function was hard on a small chunk of inputs, the new function should be hard on. Yeah. Yeah. True. Okay. I shouldn't say worst case because now we're trying to prove this to mild average case to strong average case. Okay. So we do direct product. And now the new thing should be hard on most inputs. I mean, we've all heard this statement a million times before. But we're usually used to hearing this statement for circuits, not for algorithms. Let's see what goes wrong. Okay, let's try to prove it and see where we get stuck. Let's start with an algorithm that computes the direct product well on a big chunk of inputs, like 1 over n. It shouldn't be able to do that. Let's plug in the local list decoder. It would be like the decoder with Oracle access to the usual thing, right? List decode using Oracle access to the corrupted function. And now the list decoder should compute the original function on most inputs. That's the guarantee because it's approximately correct. The problem here really is that the list decoder needs the index in the list. But without an index, it just succeeds with low probability. Okay, we don't know how to produce this index when we are a uniform algorithm by ourselves. So, okay, there's a classical patch. Not the first time people who are dealing with this have heard the notion of an instance checker. Well, let's build an instance checker. An instance checker for a function is a machine such that if you give it Oracle access to that function, it can compute the function, which is not very impressive, but it also satisfies a soundness condition. If you give it Oracle access to anything else, it either still computes the function, or it says like you're a lying liar. And outputs perp and goes on. Okay, so this is an instance checker. We know of constructions of instance checkers. They're going to lose a bit in the parameters. They're not going to be good enough for this setting, but let's pretend that they don't lose. We're going to build an instance checker in a few slides that's very good with respect to parameters. It's essentially optimal. Great, let's plug in an instance checker and see what happens here. Okay, revised approach. We built the instance checker with optimal parameters. The function is hard. Every algorithm fails with a mild average case, a chunk of inputs. Reduce it to a problem that has a good instance checker in linear time, preserve all the hardness, assume that everything works well. Now encode it with a direct product and go home. Everything works, right? The tiny little problem, okay? An instance checker works when you give it access to the original function. Here it doesn't get access to the original function. It gets hardness to something that's kind of close to it, has small corruption. With usual instance checker, this isn't a big deal. Because usually instance checkers kind of spread their queries uniformly. They make random queries. The instance checker that we will build here that has good parameters with a linear time reduction does not spread its queries uniformly at all. Like if you put in a small corruption, you can kill it. Okay, let's define a tolerant instance checker, which does exactly what you think it does. Okay, so the soundness is just as before. And if you start with a function that agrees with the original one on 99% of inputs, then you're correct on 99% of inputs. That's the definition. Let's build it. We're done, good. And I'm hiding some stuff under the rug again. Because I want to say I'm making you think of like tolerant instance checkers that are tolerant, like 99% gets you 99% or 98%. We're really going to need like something like even 1% gets you 0.9%. Because of annoying infinitely often versus almost always issues. So having said that, just to keep in mind that this notion of tolerant instance checkers, you can push it to the extreme. Let's forget about it and think about the 99% regime. Now the approach works. Okay, with a tolerant instance checker, that just do what you want to do. Start with a function, reduce it in linear time to another function that has a great tolerant instance checker, encode it with a direct product, you're done. That's the proof plan. With some little details about all the stuff that's hidden under the rug, it works. And this is the main proposition that's technical and underlying it. Every function in the class is reducible in linear time to a function, basically the same class. You're going to pay a little bit, but you're not going to be too concerned about it. The size increases, running time increases polynomially. The depth increases by something that's not important in this setting. That has a tolerant instance checker that makes queries only on the same length of input. So it's good for preserving all this IO versus A stuff. And that runs in small time, like a fixed universal polynomial in n, and all the other stuff will also be n. So once in time n to the 5, say. And I'm going to say how we build it, but I'm going to make a small tangent. There are a lot of tangents here. With some work, because this is a tolerant instance checker, it would give us a worst case to average case reduction, or mild average case to strong average case reduction for this class, which isn't a class I assume that like you spent much of your life thinking about. I haven't. But with some additional work, we can make it go through for p-space and get an optimal worst case to average case reduction for probabilistic algorithms, computing functions in linear space, which wasn't known before. The best thing that I know before is 20 years old, and it has like polynomial overhead, so you're going to lose in the hardness. So there's a function that's complete for linear space under linear time reduction and has a great tolerant instance checker, and it gives you the optimal worst case to average case. This is actually worst case to average case reduction for probabilistic algorithms versus linear space. Tangent over. I'm just going to talk about how to build an instance checker. An instance checker intuitively is a proof system, and those were built in the past by proof systems. And this one is also going to be built using a proof system, just a doubly efficient proof system. And specifically the one by Goldwasser, Kalai, and Bottler. So we're going to start with a function. We want to reduce it to another function that has a great instance checker. The input to the original function is x. And at the high level, hiding some details, the inputs to this function that has an instance checker is x, which is the exact same thing, and I and j, where I indicates a round in the doubly efficient proof system from 1 up to, say, n squared. And j indicates what is the message that the verifier sends in this round. And what the function gives back is the prover's answer, right? This is basically the prover strategy function. Pretend that the proof system is history independent, right? The prover just answers according to what the verifier said in this round. In actuality, in GKR, it's almost history independent. Like it depends only on a constant number of previous rounds, which allows us to pretend this. So if it would have been actually independent, history independent, this would have been the correct definition. It's almost so, because the response here needs to depend on like 100 J's. Let's forget about it. I will try to draw 100 J's here.
By history independent, you just mean that like if the prover's optimal strategy is the same, like with say the last few rounds, only in the transcript as opposed to the whole transcript, or what do you mean?
It might be round dependent, like the prover strategy is different in the second round and in the third round, but it doesn't. The proof strategy in the third round doesn't depend on what the verifier said in the second round. But usually you have the entire transcript and you go.
The point is like all but the last bit of the transcript can be omitted. It doesn't matter.
Yeah, exactly. And it's not really the last bit; it's the 100-bit perspective.
Sure.
Okay. Any other questions?
You can't cheat by just like having the prover always act whatever the verifier said or something like this.
Having the prover just what?
If you want independence from the third round or the first round in some sense, or totally depend on the next round, you can somehow. Okay, never mind.
Are you saying that you can construct a history independent proof system based on one in which it depends on the transcript?
I think what I'm saying doesn't make sense.
Oh, if it will make sense later, I'll be glad to hear it.
Cool.
Sanity check about the parameters here, okay? There aren't too many rounds, right? Less than the running time. So like if the input had n bits, adding this will add like log n bits, I don't care. And the number of coins that the verifier uses in this proof system isn't too large. So basically it's a linear time reduction. That's my point. Like I'm mapping this type of inputs to this type of inputs. How does the linear time reduction go? Okay, you give me X, I want to reduce to this new problem. Well, let's assume that the prover, the first thing that it does after it wakes up in the morning is say what the value of the function is. So just, okay, this will be 0 and 0 and we're done. X goes to X, 0, 0. Good. The prover is efficient. It's a doubly efficient proof system, which means that the complexity of the problem is preserved. That's the point of using a doubly efficient proof system here. Right? Deciding this new problem, the prover strategy functions, is not too hard compared to the original problem. And the verifier in the doubly efficient proof system was super efficient. That's also a property, which means that the instance checker that we'll get is also very fast. How will the instance checker work? It would do the obvious thing. It would simulate a proof system. It would say, okay, what do you say in the first round? Good. Now let me choose a message in the second round and challenge you again and again until we're done. If the prover is correct, we're good. If not, then okay, good. This is it works actually. This is a description of the entire construction. The only problem is that it's not tolerant. Right? Of course, if the prover is good, then we're going to be happy. But if like 1/n of the prover strategy functions are corrupted, then we have no guarantee. And in fact, it's not hard to construct counterexamples here for this specific proof system. Just corrupt the last 2 rounds. Okay, it's actually not a big deal. This is what I want to say. You can turn it into a tolerant thing and it's not a big deal. So instead of like having a round, let's the answer here would be the answer according to a polynomial that interpolates the polynomials in all rounds. And instead of just giving it a number of a round, we give it something in a larger domain. So now, okay, if someone is trying to corrupt this specific area.
Hiding the precise question you're interested in?
You can say that like there will be a specific question that you're interested in, but then you're going to use self-correction. So basically, you're going to spread out your queries uniformly. Is that what you're thinking of when you say hiding the question? Okay, then yes. that's it. It actually works. This is basically the description. We're done. That's a tolerant instance checker. If you want to look at the details of the instance checker, they're in the paper. They give you optimal worst case to average case reductions for linear space. And I think I have a minute, which is perfect for the open problems slide. Rahul, your open problem is the second one here. So let's start. Okay. As I said, the missing piece in hardness versus randomness, before going to this fine-grained stuff, just get BPP equals P on average from hardness in exponential time. We honestly don't know how to do it. It's a fantastic open question because we've been stuck on it for so long. After we're done with it, let's do the harder thing that Rahul wants to do. Deduce BPP equals P on average from fine-grained hardness in P, like a function in P that's hard for time n to the 10. Do the thing that Ligia wants to do. Strengthen the conclusion to BPP equals P on average instead of RP equals P. There's a fantastic open problem hiding here too. How to merge PRGs for uniform algorithms. Like just one of them works, merge all of them to a merge one that works. I know how to construct a heating state generator, just take the union, no problem. I don't know how to merge them to a PRG. And there was a bulge in the trade-off. So maybe the first thing that will lead the way to progress is if we focus on getting smooth stuff. It will generate ideas that lead us to solve the big open problems. 20 seconds late. Thank you very much.
More questions?
Sorry, maybe this should be obvious, but can you go back? There's constructions that go from hitting sets to PRGs, like the tournament construction,
Yes.
or the one.
They either work for circuits or work for black box stuff.
Great, perfect, thank you.
This is non-black box and for algorithms, and on average. So whichever, I should have mentioned that in the worst case. So whichever, like it avoids all the known stuff.
So you basically, you guys are needed twice.
Yeah, you can do
And
one.
Okay.
With advice, we call it with advice, and no one can get determined.
Russell, is your hand up? Any other questions? Hold your applause, because we're going to thank the speaker, but we're also going to thank the organizers, as is customary, but also, if you remember, this whole week started off with something that I was taken a little bit by surprise by, but it was very gratifying. And I also want to extend a special personal thank you to the organizers for that special day that they organized. So thank everybody. And thank you, Eric.